Hello and welcome back to Quantum Computation Simplified, Part 9. So in this video, we'll try to understand what is quantum annealing. Okay, it's a different type of quantum computation. Alright. So in my previous videos, you have learned a lot about the quantum computers using gate model quantum computation, right? You would have seen that we'll take the qubits and manipulate using gates and then try to get the required solution. So the gate model quantum computer is very powerful and very flexible actually. You can write, any type of algorithms can be solved. But it's hard to build with the current technology available, and it's very difficult to maintain the stability of qubits. I think in the last video I given what's the effect of this problem of stability and what are the ways of getting error and how to mitigate those errors. So, and because of these complexities, today we have quantum computers with less than 100 qubits, right? Even the big companies like IBM, Google, Honeywell, so they are unable to give, but they are working and they have a clear roadmap to come out with more number of qubits to solve a real world problem. Okay. So parallelly, D-Wave's another company working on quantum computing. They come out with a different technology. It's called quantum annealer. Okay. But it doesn't give that kind of flexibility in terms of application, but certainly it has got some good way of solving some of the NP hard problems. Anyway, that's what we'll see it in the subsequent slides. And since it is relatively easy to build a stable quantum annealing processor, so they are able to come out with nearly 5,000 qubits. Okay, and it's commercially available. You can buy a quantum annealer for your own purpose, or you can also run on their computer through cloud. Okay, before moving further, actually you need some prerequisite to watch this video, to understand this video. So it's essential to know the basics of quantum computing, like what's a qubit, what are its characteristics and things like that. If you don't know, please see my previous video, part 1 on this subject. Or you can also gain that knowledge using videos and textbooks available on this area. It's desirable to have some knowledge about quantum mechanics and optimization theory, but if you do not have, it's okay now for understanding this video. But if you want to work more on that, certainly you need those knowledges. What is quantum annealing? So this is the quantum processing unit, QPU, and this is the quantum annealer. Okay, so they look similar to what you see in IBM quantum computer, but the way they handle the qubits is different, and that's how we have a parallel approach compared to a gate model quantum computer. So this is again a quantum computing method used to find the optimal solution of problems. Okay, we will understand better as we go through that. It uses the properties of quantum mechanics like superposition and entanglement, which you are familiar. We have seen those properties being used in quantum computer, gate model quantum computer. And this uses another property called quantum tunneling. So you will anyway we'll learn this little later. So why it's called annealing actually? So it's because they use the word from material science. I think people who work on materials and mechanical engineering guys, they know that annealing is a process which helps to improve the ductility of the material and to relieve the stress in some cases. So what do? So there we raise the temperature of the material and then allow it to cool naturally. So similarly here also we are trying to raise the energy of the qubit instead of temperature, and then you make the program such that the qubits will come and settle at the lowest energy state, giving you the answer. Okay. It provides an approach for the solution of NP hard problems. Since it's less affected, so you understand less affected by noise than gate model quantum computing, more usage of qubits is possible. That's why we have seen actually 5,000 qubits qubit computer is available today using this technology. Moving further on this, so quantum annealer is a probabilistic rather than deterministic. Again, like a gate model computer. The computer returns many answers in a short amount of time, in microseconds. We not only get the best solution, but also other very good alternatives from which we can choose, based on the situation. Quantum annealer also has error. It's not that totally free from error. It has got error in terms of values of bias and couplers, which you will learn in the next slide. And it's also is prone to temperature disturbances, because the qubits are typically similar to what we have in IBM quantum computers. So they are all superconductor circuits, so which means they work at a very low temperature. So any temperature disturbances around from the environment will cause some error in the solution. So, but it's much better compared to gate model quantum computer. So what are the applications of quantum annealing? So optimization of roads. So this has been used in one of the German cities by Volkswagen. So they found it very useful. You can use this for some of the problems of machine learning, financial modeling, material science and chemistry. Basically, actually, it solves different optimization problems. In fact, you can, some people have solved factoring of prime factors of a composite number using quantum annealing. Only thing, you have to define the problem like an optimization problem. Okay. Hope you got some idea about quantum annealing. Don't worry if you haven't understood fully. You will have better explanation coming soon. So we have seen in the previous slide bias and couplers. So this is how you program it. Okay. So what is bias? So bias is trying to force the qubit to take something. Actually, so you excite the qubit to a superposition state. Afterwards, you add a bias such that it will go and settle down at 0 and 1. From 0 and 1 superposition state, it will go to either 0 or 1. And if you tweak the bias such a way that you can make it to fall, the qubit to take the position, state of 1. And what is coupler? Coupler is actually whenever you use entanglement, that means more than one qubit. Okay, so in this case, suppose we have two qubits entangled, then use the coupler to get the lowest energy. So two qubits together will have 4 possible states, right? So you program it such a way that it will come to 1 1. You declare that. That's how you program. You can force to take the qubits to the desired answer by changing the bias couplers. There's one more thing, we saw something called tunneling, right? So tunneling, we don't really do the programming, but in the hardware they make use of the quantum property. So what is tunneling is, suppose you want to move the state qubit state from 0 to 1, you don't have to climb all the way to the top. You can go through the peak. So that's called tunneling. It's a bit difficult to understand, but that's the property of a quantum mechanical element. So they make use of it to get a faster solution. Okay. The biases and couplings define an energy landscape. So given the problem, you try to build a landscape using biases and couplers, and then you hand over the problem statement to the D-wave quantum annealer, wherein they will ensure that the annealer finds the minimum energy of that landscape. So hope you got some idea about how it works. If you haven't got, maybe we will go some more explanation. So the D wave uses something called binary quadratic model. Actually, you have to convert your problem to the models given here. So again, it has got two types. One is called Ising model, another one is Cubo model, quadratic unconstrained binary optimization model. So Ising model, people who are familiar with magnetic theory, they know what is an Ising model. So wherein you try to make the spin of the atoms to get magnetized or demagnetized, right? So and then the spin directions are referred as -1 and +1, right? So same logic is being used. So you define an energy equation using this approach. So wherein we have, so these are all the states of the atom or states of the qubits. Okay, then you multiply with the constants, then sum them up, then try to minimize it. That's all you will do. Okay. In Cubo model also we will have same approach, except that there is one additional constant term, first thing, and the second thing is the state of the qubits we represent 0 and 1, I mean, which we are familiar, right? This is slightly different, but you don't have to worry. I mean, they both the models will give the, I mean, answer in the same way actually. And if you want to convert from one model to other model, you can use this equation. Literally they are one and the same. So let us see how do we formulate the problem, okay, using this approach. Okay, so our problem here we want to solve. We have 4 persons and we need to find ways to represent friends with the same value. We want to assign values such that uh, the friends should have some value, and the enemies, friends and enemies, if you, they should have a different value. So in this case, Alice and Bob are friends. Similarly, Charlie and Dave are friends, but Bob and Charlie are enemies or foes. Okay. So let's start building the model. So how do we assign the values? First, let's build the model for Alice and Bob. Alice and Bob are friends, so they should have same values. So let's say X and Y represent the values of possible values, I'm sorry. Okay, so whenever the values are same, we will say that is -1. So minus, I mean, it can be any arbitrary number also, but for simplicity we will say -1, and we declare that that is the lowest energy. When they have different values, that is 0 and 1 or 1 and 0, we'll declare it as 0, so which is a larger number compared to -1, right? So when 1 and means lower energy, okay. And now this is the value of the Cubo model. The Cubo model is given in by this equation. So we have a constant C, that's what is given here, C plus AI QI sigma. So we have two qubits, so A1x, A2y, okay, and we have one quadratic term, that is BXY. So the advantage of this approach is we will not go to the higher order terms, we will always go with the 2 or the second order terms. So BXY, since there is only one B, we have put B instead of B1, B2 like that, okay. Now I have an equation. I have the values of X and Y, and we need to get the values of A1, A2, B and C. So let us see how we can get. So X is 0, so this term will become 0, and Y is 0, this term again 0, this is also 0. So C is equal to -1. So that's how this equation came. I mean, this is simplified by assigning the values. So the next, X is 0, gone, Y is 1, so A2 will be there, A2, XY is 0 plus C. So A2 plus C is equal to 0. So that's what it has come from here. Similarly, it will come from here. And the last one is all are 1, right? So A1 plus A2 plus B plus C equal to -1. So that is what has come from here. So now we have 4 variables, A1, A2, B and C. and 4 equations, so we'll be able to solve. So the solution is given here. C equal to -1, A2 equal to +1, A1 equal to +1, B equal to -2. Now if you substitute in this, so you will get x plus y minus 2xy minus 1. So our model is ready for Alice and Bob. So the same model can be used for Charlie and Dave because they are also friends, right? Now we need to get a model for Bob and Charlie. So in the next slide we will see the model for Bob and Charlie. In order to avoid confusion, instead of x and y, I will call it as z and w. So these are all the combinations of possible. So since they are enemies, so you should have, when they have same values, it should not be at the lowest energy. But when they have different values, that should be at the lowest energy. So that is what is given here. So this model equation has come from here, like in the previous case. Now we need to evaluate and for the values of z and for w, and we get 4 equations like this. Like the first case is 0, w is 0, so this will become 0, this will become 0, so only f is left out, f is equal to 0. So in the next case it is z is 0, so nothing, w is there, so d2, this is 0, d2 plus f equal to -1, okay. And similarly d1 plus f equal to -1. The last one is we'll have 1 1, so d1 plus d2 plus e plus f equal to 0. So we have 4 equations. You can solve for these 4 variables. We have got an answer, and this is the, by substituting this equation, we get by substituting these 4 parameters, right? -1z minus 1w plus 2zw plus 0. So we have got equations for friends and enemies, okay. So afterwards we have to build a graph. So the graph has got a node and edge. It's called, the node is a linear term, or the qubit, I mean it represents a qubit, or bias we can call. And so this is the coupler, the edges, which gives the relationship between the 2 nodes or 2 persons, okay. So we got the first equation came from the previous slide. So plus 1x, right, minus 2xy plus 1y constant. So constant, we will keep it away from the graph for the time being. And these two are enemies. So this has come from here. Minus 1 z minus 1 w plus 2 zw, okay. And this is same as the previous one here. So my plus 1 minus 2 between the coupler value and the node value. But in this node, if you see, you have 1 plus 1 and minus 1, so they get cancelled. Similarly, this plus 1 and minus 1 gets cancelled, and the graph looks simplified with this representation. So what is this? You have x, okay, we have 2 constants, so that is what is written here. So this is the combined equation. So you have constant minus 1 minus 1, so you have minus 2, 1x minus 2xy, so these two are 0, so we'll forget. So and this is 2yz minus 2zw and w. So now we have Cubo model for the complete objective. Now what is our duty? We have to make use of quantum annealer, give this model, it will give you solution with probability of different combinations, okay. So when you evaluate the Cubo model, so we have 4 persons, right? 4 set of qubits. So there are 16 combinations possible, 2 to the power of 4. And then whichever is giving the least energy, that is our solution. So of course I have not given all the solutions here for want of space, but you can see here in the given set of solutions, 2 least energy solutions are possible. So let us say, let us check whether that combination is meeting our objective. The objective is friends should have same values. Alice and Bob are friends, so same value. Charlie and Dave are friends, they have same value, but these two are enemies, so they have different value. So this has met the objective. Let us check on this line. Alice and Bob are friends, same value, good. Charlie and Dave are friends, having same values, good. Then Bob and Charlie are having different values because they are enemies. So we'll be able to, we are able to solve this. Since it's a small problem, possibly you can do it with the trial and error, but when the problem is very complex, quantum annealer is very useful. So in order to get the potential solution and the nearby solution, so that's how it is useful. The one big difference is actually we work at a slightly higher level. So we define the problem, we build the model and give it to them. We literally do not manipulate each qubit the way we did in gate model. So that's the difference. So they have given a lot of functions, D-Wave guys, and you can get free access. So this is a typical D-Wave computer with all low temperature system, everything put together, including the quantum processing unit. And you can get free access by signing up at this site, and you get free time, 1 minute of processing time. So you'll be surprised, 1 minute of direct access. So don't worry, 1 minute is really a good amount of time because each problem takes a few microseconds. So you will be able to solve many problems, and this is for free, and there are other different plans available for paid customers. So if you want to solve, once you are familiar with this approach, you can get some more time by paying to D-Wave. Of course, you can also get extend the free time by giving some open source support. Unfortunately, I have exhausted my time, and so that's why I didn't implement this. But it is very simple. So you define your equation and call their functions, you will get the solution. So that's all about annealer. I know that I'm sorry, I'm not gone to the depth with the real world problem, but this is just to give an idea. Possibly later I'll come back with more deeper understanding. Okay. These are all the references which are good for all of us. So the documentation is really extremely good from D-Wave system, and Wikipedia is as usual very good to give an introduction about that. And there's a nice video again from D-Wave system. In fact, a set of videos. If you go there, you will get connection for the other videos. They explain the annealing process very nicely. They also, there's another video again from D-Wave which gives how do you program it. In fact, I did a lot of search on the textbook. I couldn't get other than this one. Unfortunately, I couldn't study that. Hopefully, it is good. But there are plenty of papers. If you search for quantum annealing, you will see plenty of papers to know more about the quantum annealing and to know about more applications. That's all about. So what next? You can explore quantum annealing further with D-Wave documentation and videos available. You can start looking into optimization problems which can be tried with quantum annealing. There are many problems which can be solved. You can do that. I will try to learn, start getting into the depths and come out with videos on quantum computing which will be useful for your learning as usual. And I'll come back to quantum annealing later after doing some more work on gate model quantum computer. So thanks for watching. So hope we'll be able to meet again. Till then, goodbye and thank you.